What if I told you that after several centuries of hard work, mathematicians and statisticians have figured out that if we have a bunch of random data, like people's seat preferences at a theater, we can instantly figure out the probability of someone picking a random seat just by knowing how the data curves. Our eyes and brain can work together to make sense of things we see, like shadows or lines or areas, without having to know every precise detail. And we can use this same power when we fit lines and curves to data plots. By exploring some special shapes, it turns out we can make sense of large amounts of information without having to know what each and every data point actually is. I'm Jason Guglielmo, and this is Study Hall Real World College Math. Let's say you're at a movie screening and there's 25 chairs lined up in a straight row, and no matter which seat you choose, you'll be able to see the entire screen easily. The probability of you choosing any one of those chairs is 1 out of 25, or 4%, because you have 25 equally good options and you can only choose one at a time. That means the probabilities are uniform, constant. We can plot this information too. There's a 4% chance you'll choose the first chair, a 4% chance you'll choose the second chair, and so on. Now we can draw a straight line skimming the top of all the bars, and even write an equation for that line and say y equals 1/25th, or use the special function notation and say f of x equals 1/25th. We now have a curve that emphasizes that no matter what data point or x we input, which in this case is whichever chair you choose, the probability of choosing that chair is always 4%. There's one more thing we can notice about our plot. If we add the probability of each event together, that's 4 hundredths plus 4 hundredths plus 4 hundredths 25 times, we get 1, which makes sense because you have to choose one of these 25 seats in the theater. And here that's the same as adding up the area of each bar. In fact, this is true in general. The probabilities for all the outcomes of an event add up to 1, because one of those things has to happen. But it's different when you're trying to pick which row to sit in at a movie theater. Our friend Erin is thinking about this too. She's planning a premiere for her new food documentary honoring some of her favorite recipes made by women in her life. She even managed to book the local black-owned theater that once played the greats back in the day. It's a cool space, and the seats in the theater are arranged like an opera house, with rows lined back to back from the stage to the rear. That means each row will have a different vantage point. From row to row, the probability of someone choosing a seat is going to be different. And if we plot the probabilities again and focus on rows this time, that will change the heights of our bars. Erin is expecting at least 100 guests and wants to make a seating chart. So she asked her assistant to pull some old survey data from her past movie premieres to figure out everyone's row preference. When we plot the data, it looks a lot different than our example from before. But if we think about it, that makes sense, because it's less convenient watching a movie the further away you get from the center. On our plot, these sections have a very short bar that we can actually barely see unless we zoom in. Few past guests preferred those seats. Erin also expected most of her guests to want to sit in the middle row. The middle row gives that ideal angle, not too far from the exits to run to the restroom, the audio is crisp, and it can feel like the whole screen is just for you. That's why the center row has the tallest bar. If we draw a line outlining the top of this data, instead of a straight line like before, we have this bell-shaped curve, which is symmetrical around a center point. A bell curve usually indicates the data has what we call a normal distribution, though the exact shape of the bell can change depending on the mean and standard deviation of the data. For Erin's premiere, let's refer to the middle row as row 0. Based on her data, this is the average row preference, the most likely to be chosen, and the row that's literally in the center of them all. In other words, the middle row is the mean, mode, and median all at once. And for an ideal normal distribution, the mean, mode, and median are all equal. We can also talk about the standard deviation, or broadly how far each data point is from the mean, which in an ideal normal distribution equals 1. Altogether, when normally distributed data has a mean of 0 and a standard deviation of 1, we say the curve outlining the data is a standard normal curve. And just like how in our first plot, the area under the curve showed us the probability of each seat being chosen, we can also use this curve to find the probability that different rows are chosen. Let's do an example. Say we want to know the probability of a guest wanting to sit closer to the screen. Let's say we define that as sitting in the row right next to the screen up to row 0 at the center of the theater. We can look at every data point to the left of row 0 that's under the curve and above the x-axis. That's 50% of the area under the bell curve, and 50% of the data is represented in this space, which translated into a 50% probability of a guest wanting to sit in row 0 or lower. And for Erin, all of this is great news. This means her guest seat preferences are not only typical, they're predictable. Like, say she wants to know the probability of people flocking to the middle rows, the center row, the row above it, or the row below it. Mathematically, that's the mean row and the two rows that we'll say are within one standard deviation on either side of the mean. If we calculate the area that's under the curve, above the x-axis, and bounded on both sides by the rows that are one standard deviation away from the mean, that's 68% of all of the data. So 68% of the data lies within one standard deviation on either side of the mean. In fact, this is the case for any set of data that's normally distributed, and part of what makes normal distributions so useful. Things are predictable and easy to analyze. Then, if we expand out another row on each side, the probability of choosing any one of those 5 center rows is 95%, because 95% of normally distributed data is squished within 2 rows, or what we're calling 2 standard deviations of the mean. And if we expand out one more row on each side, then the probability of choosing any one of those 7 center rows is 99.7%, because the 99.7% of normally distributed data is squished within 3 standard deviations of the mean. Knowing how much data is squished between our first, second, and third standard deviations is sometimes called the 68, 95, 99.7 rule, or the empirical rule. Now, I have to admit that this movie theater example isn't perfect because we don't have the option to sit with all the stale popcorn in between 2 rows. That means that not all data, I mean people, can be perfectly squished within 1, 2, or 3 standard deviations/rows, and we were a little hand-wavy before in order to illustrate our point. So for this next example, let's instead imagine that Erin wants to install a large confetti machine that will release food-shaped confetti at the end of the screening. She wants it installed right above row 0. The confetti could land anywhere, but most of it will land on the center row, and gradually less of it will reach the other ends of the theater. So the spread of how the confetti lands follows a normal distribution. And to see the different probabilities of where confetti will land, we're going to introduce a tool called a z-score. Basically, the z-score of a data point is a single number that tells us how many standard deviations away from the mean that data point is. Since the z-score tells us about the standard deviation, as we just saw with the empirical rule, we can then use it to find the probability a data point would fall in a particular area under the bell curve. Now, one of the special powers of the standard normal distribution is that because the mean is 0 and the standard deviation is 1, every value already represents how many standard deviations it is from the mean. So again, let's assume each row represents 1 unit of standard deviation, and let's label everything below the center row with a negative z-score, and everything above the center row with a positive z-score, based on how many standard deviations they are from the center row. So when we're 0.75 standard deviations above the center row, we have a z-score of 0.75. Now, mathematicians have played around with the standard normal curve for a long time, and figured out that this function describes the bell curve of the standard normal distribution. And they've also made finding the area under that curve a lot easier by creating a z-score table using that function. Some tables are slightly different, but often this table calculates the area under the standard normal curve to the left of the z-score, which we know from our past examples tells us the probability a data point falls in that area. So once we turn each row, or possible spot confetti could fall, into a z-score, we'll know the probability of being drowned in confetti at that spot. We'll talk next episode about how to find the z-score of a data point that's normally distributed, but doesn't have a mean of 0 and a standard deviation of 1. To use this z-score table, we first look down the leftmost column and find your z-score up to the 10th place. Then we go along the row until we reach the z-score's 100th place. So the area underneath the standard normal curve to the left of a value that's 0.75 standard deviations above the mean is 0.7734. So the probability of confetti falling on the area 3/4 above the center row, or any row below that, is roughly 77%. Notationally, we'd write that as the probability the z-score of the data is less than or equal to 0.75 is about 77%. But say Erin reserved the row exactly 2 rows behind the center row for her close friends. Using the z-scores and a bit of geometry, she can also figure out the probability of her friends getting covered in confetti. Let's say we want to know how much confetti would land between the area covered from z-score 1.1 to 2.9, since row 2 would be right in the center of that. The z-score table isn't really built for finding the area between 2 points, but with a little geometry, we can make it happen. The probability of confetti landing at location 1.1 or lower covers 0.86433 of this total area, which is about 86%. The probability of confetti landing at location 2.9 or lower covers 0.99813 of this total area, which is about 99.8%, but not quite 100. Since these two areas overlap, we can subtract the area that z-score 1.1 covers from the area that 2.9 covers to get the section we're interested in, which is 13% of all of the area under the bell curve. So there's a 13% chance that Erin's friends will be rained on by yam and broccoli-shaped confetti. Statistics and probability are pretty close friends. The shape of statistical data on a plot also tells us the probability of that data happening again. Data that follows the shape of being normally distributed is predictable. When our data has a mean of 0 and a standard deviation of 1, we can rely on the z-score to point out the probability of any event happening. By finding the area squished between the bell curve, the z-score, and the x-axis, we can read the z-score table to give us that probability, but only when the bell curve is a standard normal curve. Again, there's not many real-world instances that fit the standard normal curve situation, but in theory, the theater helped us get a good enough viewing of how it's intended to work. In our next episode, we'll dive into how to use the standard normal distribution and the z-score to quickly find the probability of real-life events when the mean isn't 0. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you liked this video, give us a like and subscribe. You can learn more about ASU in the videos produced by Crash Course in the links in the description. See you next time.